Hi, I am Illyoung Choi at University of Arizona. I'll be talking about my research paper, Stargate, Remote Data Access Between Hadoop Clusters. Scientific computing is a research activity that uses computing capabilities to solve complex scientific questions. Big data analysis, machine learning, and computer simulations are examples of scientific computing. There are four trends in today's scientific computing. Today's scientific computing is becoming increasingly data-centric and collaborative. The data-centric and collaborative research paradigms have increased the scale of data, so increasingly more computing resources are required to process the data. This resulted in the wide use of cloud computing and cluster computing. The four trends in scientific computing have caused several challenges. First, data-centric research requires increasingly larger datasets from a variety of data sources. Providing remote access to the datasets is becoming increasingly challenging. Second, collaborative research paradigm requires increasingly more data transfers between geo-distributed collaborators. Third, cloud computing also requires increasingly more data transfers between remote systems. Lastly, cluster computing makes efficient remote data access more challenging because it relies on distributed computing resources. Orchestration of distributed resources is more difficult than doing it in a single machine. Stargate is a virtual file system that provides efficient on-demand data transfer in a cluster computing environment. Stargate uses on-demand data transfer rather than staging. Staging is the current dominant method of remote data access in scientific computing. In this paper, I propose use of on-demand data transfer in scientific computing for more efficient remote data access. Stargate provides convenient access to a variety of data sources via common data access interfaces. Stargate also provides efficient inter- and intra-cluster data transfer. Stargate uses several strategies to provide efficient remote data access over WAN in a cluster environment. First, Stargate uses on-demand data transfer. On-demand data transfer eliminates transfer of data parts that are ultimately unused. It also does not create permanent local copies, which requires active management. On-demand data transfer also allows computation and transfer to overlap, so it can use computing resources more efficiently. Second, Stargate provides common data access interfaces. Scientific computations can make direct access to a variety of data sources via the interfaces. Third, Stargate uses cluster-to-cluster data transfer to make efficient use of cluster's total bandwidth. Fourth, Stargate implements WAN optimizations. WAN optimizations minimize WAN traffics required. Also, they improve data transfer performance. Lastly, Stargate orchestrates computation, data caching, and data transport to eliminate unnecessary intra-cluster traffics. Doing so, it improves end-to-end data access performance. Stargate consists of two parts, client and server. Stargate client provides a data access interface to computations, and it communicates with the local Stargate server. Stargate server implements core storage functions. It implements a peer-to-peer architecture to provide scalability and fault tolerance. Stargate server uses a distributed hash table co-located on the same cluster for storing internal data. Stargate server does not store actual data. It communicates with the storage on the same cluster, such as HDFS, to provide data access. Stargate server communicates with remote Stargate servers. Stargate implements several data transfer optimizations to improve data transfer performance. Stargate uses a HTTP-based data transfer protocol to take on advantage of existing web infrastructures, such as content distribution network. Stargate also implements a content addressable protocol for data transfers between Stargate servers. A file is chunked into large fixed-size blocks, and the blocks are named using a cryptographic hash function. In doing so, a data block is retrieved by the block name instead of file path and the offset. If the block content is updated in a remote storage, the block name also changes, so access to the block with the old name must fail. So it prevents reading inconsistent data blocks. Also, if there are multiple blocks containing the same content, they will have the same block name, so redundant data transfers can be easily detected and prevented using the data cache. Stargate also provides large cluster cache. Stargate caches recently accessed data blocks using a distributed hash table. The distributed hash table provides large capacity since it distributes caches over cluster nodes equally. By caching as much as data, Stargate provides increased chance of data reuse. Stargate also prefetches data blocks that will be accessed soon. Prefetching improves data access bandwidth. Stargate prioritizes on-demand data transfers, then prefetch data transfers to respond to data access requests from computations quick. Lastly, Stargate uses concurrent data transfers. Transfers are performed using all cluster nodes, and the transferred data are stored in the distributed hash table for later use. Stargate co-locates computation, cache, and transfer to minimize unnecessary intra-cluster data transfer. In a storage cluster, the storage node and the transfer node may be different. In this case, LAN traffic is required for data access. To address this problem, Stargate uses data block layout of an underlying storage system to co-locate transfer and data. In a compute cluster, transfer node, storage node, and compute node may be different. This occurs when compute, storage, and transfer systems are not integrated well. In this case, LAN traffics are required. Stargate addresses this problem by vertical integration of services. Stargate uses the distributed hash table as a rendezvous point for co-location of computation and transfer. Stargate first determines which node in the cluster will cache a data block. Then the transfer and the computation of the block are co-located on the same node. This design guarantees that computation can be co-located with their input data, even when data are not present in the computation cluster yet. This works. To evaluate Stargate performance, I deployed Stargate on Google Cloud Platform, one in Singapore and the other in Virginia, United States. Then I performed 4 different benchmarks on the compute cluster. TestDFS.io is a popular I/O benchmark for Hadoop. TestDFS.io Plus I used in this paper is a bug-fixed version of TestDFS.io. TerraSort is another famous Hadoop benchmark that measures sorting performance. Libra is a realistic DNA sequence analysis app. I ran it with 2 different parameters, k equal 1 and 8, for different workloads. K equal 8 has a higher, heavier workload. Stargate performance is compared to existing remote data access methods. WebHDFS provides on-demand data access. DistCP is a popular tool for staging. Local HDFS is also used as the best case scenario because it stores all data in the local cluster. In the graph, the yellow, blue, and green bars show the performance of Stargate with different states of intra-cluster caches. For all benchmarks, DistCP, shown as orange bars, was the slowest. HDFS write bandwidth became a bottleneck, and the transfer distribution at file level granularity was inefficient. Also, computation and transfer could not be overlapped, so compute resources had to sit idle during file transfer. Stargate was faster than WebHDFS that provides the same on-demand data access regardless of cache states. This shows that Stargate provides improved end-to-end data access performance. Stargate performance was even comparable to local HDFS for TerraSort and Libra k equal 1 case. Stargate was 8% slower than local HDFS for Libra k equal 8 when it had cold caches, but it still was faster than existing remote data access tools. When Stargate had all data cached, which means Stargate hot, it showed the same performance as local HDFS for TestDFS.io Plus and TerraSort. Generally, Stargate outperformed the existing remote data access methods. This graph shows how much WAN traffic is required during the benchmarks. This is important because WAN traffic not only impacts the runtimes of scientific workflows, but also impacts the data transfer cost. The graph shows that Web HDFS required the most WAN traffic. One reason for this is Hadoop often creates redundant compute tasks, so they caused redundant data transfers. Stargate doesn't require redundant data transfers because it caches data blocks in the compute cluster using the distributed hash table. Also, line-oriented computations reading the beginning of the next blocks, so this caused more data transfer than Stargate. Stargate avoids this by having small overlaps between consecutive blocks. So Stargate doesn't need to read the next blocks actually. This technique is described in the paper more in detail. When Stargate had cold caches, its cost was almost the same as this CP. Stargate required only 0.1% more WAN traffic than this CP because of the overlaps and the communication overhead. When the Stargate had warm caches, it reduced WAN traffic about 30% because 30% of data were cached. When Stargate had all data cached, WAN traffic is not required, so it's not present in this figure. This shows that Stargate was faster and costless To sum up, Stargate implements on-demand data transfer and showed on-demand data transfer can be a better option than staging. To address drawbacks of on-demand data transfer, Stargate implements several transfer optimizations to improve data transfer performance. Lastly, Stargate co-locates computation, cache, and transfer on the same node using the distributed hash table as a rendezvous point. This eliminates LAN traffic on the compute cluster, so it improves end-to-end data access performance. Altogether, Stargate provides fast and costless remote data access to scientific computing. Thank you.